Hello students, in the previous video we have studied about the relation between stress and strain in the Hooke's law, and also we have studied about elastic limit. And from Hooke's law we got the value that the modulus of elasticity, that is K, was equal to stress upon strain. And earlier in the first video introduction part, we have studied about three types of stress, and simultaneously we have studied about three types of strain. So here we will discuss about the relation among all those things that we have studied. The first part is in the modulus of elasticity is Young's modulus. So here we will see Young's modulus in stress and strain part. There we have studied longitudinal strain along with tensile stress. It is tensile. Okay? Tensile, or we can also consider it to be as compressive stress divided by longitudinal strain. That is, modulus of elasticity is equals to stress upon strain. If we write tensile stress upon longitudinal strain, then we get the Young's modulus, that is stress is equals to restoring force acting per unit area divided by longitudinal strain. We have studied the formula. This is change in the length divided by the original length. Therefore, Young's modulus is equals to, finally when we simplify it, we get restoring force multiplied by the original length of the material divided by area of cross section multiplied by the change in the length of that material. So this is Young's modulus. Here the unit is equals to Newton meter divided by meter square multiplied by meter. So finally we get Newton per meter square, and the dimensional formula will be ml minus 1 t minus 2. Similarly, you can find the unit and dimension of the other modulus of elasticity as well. We will not discuss about it because this is just a waste of time. You know how to find the units and you know how to find the dimensional formulas as well. So here, this was what Young's modulus is. So the next part is bulk modulus. Bulk modulus is equals to, again, this is modulus of elasticity, the volumetric stress upon volumetric strain. The stress is equals to restoring force acting per unit area divided by volumetric strain, that is change in volume divided by the original volume. And finally we get, after simplifying it, that is bulk modulus is equals to force multiplied by volume divided by area into change in volume. So let us consider this is equation 1, and now let us see the case of gas. If we have gases, in the case of gases, we know that pressure, that is small, let us consider here it is small pressure acting on any body, is equals to force acting per unit area. Therefore, force will be equal to pressure multiplied by the area. Here, from equation 1, we can write bulk of modulus is equals to force. Force is equals to delta P multiplied by A into volume divided by A into delta V, where A and A gets cancelled, and finally we get to the conclusion B is equals to delta P dot multiplied by V, that is volume, original volume of the gas divided by the change in volume. Let us consider this is equation 2, and from here we will proceed further when we, hello students, so from where we study about the Boyle's law, we got to know that pressure multiplied by volume is always constant in the case of gases. And here when we differentiate this equation, P dot V, that P will be constant, differentiation of V plus V will be constant, and we will differentiate P. This is the process how we differentiate the things, and the differentiation of constant is equals to 0. So finally we can write it as delta P into V is equals to minus of P multiplied by delta V. So finally we can get minus P is equals to delta P into V divided by delta V. From second equation and third equation, when we compare it, in second equation it was B is equals to delta P into V divided by delta V, and here in this third equation we get my delta P into V divided by delta V is equals to minus of P. This minus negative sign is nothing other than the logic that if we increase the value of P, the value of V will decrease, and if we decrease the value of P, the value of V will increase. So this is how, when we compare equation 2 and equation 3, we get to know that bulk modulus is equals to pressure in the case of gases. ठीक है? So we can write, in case of gases, case of gas, bulk modulus is equal to pressure. Clear? We have concluded from the derivation that we have made. And finally, there is modulus of rigidity. We have studied about shearing stress and shearing strain. So modulus of rigidity will be equal to shearing stress upon shearing strain. Shearing stress is equals to restoring force upon acting per unit area divided by shearing strain. We have denoted shearing strain with the symbol theta, and where this force acting on the surface area is tangential to the surface. Tangential to the surface, we have discussed it. Let us consider, after applying this force, this tangential force, the object is displaced by an angle theta, and let us consider this linear displacement is delta x, and let us consider the height of the object is h. So this can be written as theta is equals to, we know the formula, it is equals to arc upon radius, that is delta x upon radius we have considered h. So from this equation, when we put the value of theta is equals to delta x upon h, and when we simplify it, we get G, that is modulus of rigidity, is equals to force multiplied by the length of the body multiplied by the linear displacement created due to this tangential force multiplied by the area of cross section, and this is the area where the force has been acting on. So this is what we have to study about the modulus of elasticity, and this is all for the video. Thank you very much for watching it.